With our arithmetic sequences and series, we were able to take advantage of that repeated structure to come up with a formula that saved us a lot of time, some patterns that showed up. Let's see if something similar is going to happen here with our geometric sequences and series. All right, what is the first some of the first 5 terms of the sequence here? So first off, we need to recognize that this is in fact geometric. So it's times 2, times 2, times 2, and if we go times 2 again, that 5th term would be 48. So we can take the 3 plus the 6 plus the 12 plus the 24 plus the 48. This isn't so bad. This is a nice short list. So let's do 3 plus 6 plus 12 plus 24 plus 48. I came up with 93. Nice. That's not so bad. Let's now move on to this next one. What is the sum of the first 20 terms of the sequence? Here's where my lazy is starting to kick in. I have no desire to find 20 numbers and then go back and add up those 20 numbers. I'd like to see if we can take advantage of the structure here to find a shortcut. And let you know something, we're going to be able to. Here it goes. Instead of writing this as 3 and 6 and 12, I'm going to write them this way. This is just 3. This is 3 times 2. This is 3 times 2 times 2, which is 3 times 2 to the second. To get to the next term, you multiply by 2 again. And to get to the next term, you multiply by 2 again. Notice that all of these terms are just 3 times 2 to ever increasing powers. So let's take advantage here of that. The sum of the first 20 terms is going to be the first term plus the second term plus the third term plus all the way up through the 19th and 20th terms. Now here's the thing. Notice how the exponents, so the first term had no 2's. The second term had 2 to the first. The third term had 2 to the second. So the exponents on the 2 are always 1 lower than the term number itself. So the 19th term will actually be 3 times 2 to the 18th. And then the 20th term will be 3 times 2 to the 19th. Now, at this point, you may be thinking, it looks to me like you just made things more complicated. As is often the case, it's going to get a little messier before it gets a lot less messy. The next thing I'm going to do is this, and I need you to trust me a little bit because I've seen this work before and I know it's going to come out in the end. We're going to look at this same sum again, but I'm going to multiply everything here by that common ratio, and here our common ratio is 2. I'm going to multiply everything by 2. So multiply by 2 on this side, and now multiply by 2 on this side. So this first 3 now becomes 3 times 2. And just to be consistent here, I'm going to line it up under this 3 times 2. This term becomes 3 times 2 to the second because we're multiplying by another 2. I'm going to line it up under that 3 to the second. We're going to continue doing that all the way down the line. So we'll have here the 18th term, 3 times 2 to the 17th times another 2 is 2 to the 18th. Then this term will become 3 times 2 to the 19th. And this term will become 3 times 2 to the 20th. Okay. What makes this work, and this is, again, a fantastic little trick, is if I've got this repeated, this repeated, this repeated, everything is repeated except for the very beginning of the top list and the very end of the bottom list. So something magic is going to happen if we subtract them. We take the top row minus the bottom row. S minus 2s, where s is the sum, well, that's just negative 1s. Over here, 3 minus nothing is just 3. But this minus itself goes to 0. This minus itself goes to 0, goes to 0, goes to 0. The only other thing that's left is going to be a minus 3 times 2 to the 20th. Let's get that 2 in there. So 3 times 2 to the 20th. The thing is, I don't want negative s. I want regular s. So I'm going to come over here just for space reasons. If I take both sides, divide them by -1, this is going to give us the sum of the series. And that's a much simpler calculation to do. I'm just going to pull up my handy handheld graphing calculator and do 3 minus 3 to the 20th, which is, that's a big one, -348678438, and divide it by -1, which is going to make it positive 3, 4, 8, 6, 7, 8, 4, 3, 9, 8. This is a big one. One thing you will find is that these geometric sequences, the numbers can get very big very fast. And so if you're adding them all together, you're going to get a sum that is also very big. So what are we at here? 3,486,784,398. I don't know about you, but I think I would much rather use a shortcut like this than actually listing out those 20 or maybe 40 or 50 or 100 terms each time and trying to figure out what they are and add them all together individually. So it looks like a shortcut can exist. Let's generalize it. And by that I mean, what if instead of this particular sequence, it's any geometric sequence? And what if instead of the first 20 terms, it's the first n number of terms? I want to run through a similar analysis. Now, I would like it if you understood everything we do. It's okay if you just kind of follow along and trust the end result. The first term of a sequence is always just the first term of the sequence. In a geometric case, the second term is that first term times the common ratio. The next term is the first term times the common ratio squared. And that will continue all the way through the first term times the common ratio to the n minus 2. And then lastly, the first term times the common ratio to the n minus 1. So that kind of fits with what we saw up here. The first 20 terms, the last exponent was 1 below that. So for the first n terms, the last exponent on r will be 1 below that. All right, let's now apply this same trick. I'm going to take this entire sum and multiply it all by this common ratio. So from case to case, whatever the r is, that's what I'm going to choose to multiply by. That makes this first term look like this. Makes this second term look like this. On and on down the line until we get to the very end. And if I multiply by another r, this will just become a1r to the n. Now the final trick, because there's so much repetition, we are going to do a subtraction. Let me get just a little more space here. So s minus rs, I'm just going to write it like that for right now, s minus rs equals a sub 1 minus nothing. So the first term of the sequence. a1r minus a1r goes to 0, goes to 0. All of them go to 0 up until the very last one. Minus, because it was in the subtraction line, a1 r to the n. Next up, we're going to factor out some greatest common factors. Now, I need you to remember what you did last year and what we did at the start of this year. Factoring out a GCF just means recognizing, hey, these both have an s in them. So do the distributive property in reverse. S divided by s is 1. Rs divided by s is r. So this is, like I said, distributive property backwards. If you multiplied the s back through, you get back where you started. Over here, do the same thing with the a1. a1 times 1 minus r to the power of n. Let's not forget what we're after. The whole point of this, the goal, was to find out what the sum is. So let's take this 1 minus r and divide it over to the other side. And here, my friends, you have a very powerful shortcut. The sum in a geometric series is just the first term times 1 minus the common ratio to the nth power, where n is the number of terms you're adding up, divided by 1 minus r. So let's go back here to our toolkit page. Here's that shortcut that you can fill in. Next up, we're going to practice using that to save ourselves a lot of time.